Hey everyone, and welcome back to the series on elementary probability and statistics. In this video, we're going to continue our discussion of probability mass functions on discrete random variables. We're going to be focusing on three very important types of distributions in this video, and we're going to give a couple examples on each of them. The first distribution we're going to be looking at is the geometric distribution, followed by the binomial distribution, and then the Poisson distribution, which are pretty much similar to one another, but each has their unique characteristics. We're just going to be giving the properties of them, not proving them, giving an example, and at the end of the video, as always, we're going to give you some practice problems to work on just to test your understanding. Let's get started. Alright, so the first distribution is going to start off this way. Let x be the number of independent Bernoulli trials until the first success occurs. A couple terminology things, just in case you do not know. Independent means the probability of one event does not affect the outcome of another. Bernoulli means you can only have two different types of outcomes, success or failure. And first success means, all of the ones before this particular trial is a failure. So let us just state a particular example for which this type of distribution is going to apply. For example, if I want to find the probability of an event such as this, a bunch of failures ending with a particular success, this is going to correspond to the probability that x is going to be equal to 1, 2, 3, 4, 5, 6, and 7. So every time we have this type of distribution where all of these trials are independent of one another, this is going to be called a geometric distribution. Okay? So if I want the probability that x is equal to 7, I will have 1, 2, 3, 4, 5, 6 failures followed by one success. So I'm going to define my particular probability p. So let p be the probability of success. Then we can find the distribution, the geometric distribution, actually pretty easy to derive. So the probability that x is equal to little x is going to be equal to 1 minus p to the x minus 1, so there's x minus 1 failures there, followed by one success at the very end. So this is what we call the geometric PMF, for the geometric distribution. All right? So notice that the domain of this particular function p, or the support of the random variable, is going to be the positive integers. So 1, 2, 3, 4, and it's not bounded above. It's possible that you fail 5 million times and succeed on the one after. Right? Just unlikely. Since it is a random variable, x, it has a mean and it has a variance. So the mean of a geometric random variable is going to be equal to 1 over p, and the variance of this random variable is going to be 1 minus p all over p squared. Okay? I'm not going to prove these two properties for you, but if you're familiar with the moment generating functions, you can derive the moment generating function for a geometric random variable. Differentiate once, plug in 0, find ex. Differentiate twice, plug in 0, find the second moment, and from our typical relationship, find the variance if you're interested in those things. So those are just the basics of this geometric PMF. So let us take a moment and look at a particular example in real life that we could actually use this particular distribution for to solve. All right, consider this example. Suppose that on average you like 72% of the restaurants that you go to. If you liking one does not affect the outcome that you like another, what is the probability that it takes you 10 restaurants until you dislike one of them? So let's just pick apart this problem and understand why we're going to use a geometric distribution to find this particular probability. Firstly, you liking one does not affect you liking another. This implies independence. In the real life type of problem, typically, if you do not like one and immediately go to one after, most of the time you will be in a bad mood, and it might affect your likelihood of liking them. You might be a little bit more picky, or your expectation might increase, or possibly decrease. So realistically, there will be some dependence on these types of problems, but if it doesn't say something like this, most of the time they hope that you assume that it's independent, else it's a little bit more difficult. Now, there are Bernoulli trials. Either you like them or you do not, so only two possible outcomes. And what about the structure of the sequence that we're looking at? So we're looking at a bunch of restaurants, So what is the probability that it takes you 10 restaurants until you dislike one? So we have like. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and dislike. Okay? So we convert this to successes and failures. So I want this to be in the form failure, 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 success. All right? So what is my definition of failure in this particular scenario? Actually, let's define this in terms of success, since that's what geometric is defined. So this last event is going to be our success, and we're defining our success to be dislike restaurant. So dislike restaurant. So what is the probability of success? So it's given that I like 72% of them. So the probability that I dislike them will be 28%. Okay? So this is structuring things in terms of the geometric distribution. So now that everything matches, now I can solve. So therefore, the probability that x is equal to 10, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's the 10th value. That's when our first success occurs. This is going to be equal to 1 minus p to the x minus 1 times p. That's the general structure. So this is going to be equal to 1 minus p, so that's going to be 72%, to the power of 9 times 0.28 to the power of 1. That is going to be my probability, and you can find that it's going to be approximately 0.0146, or about a 1% chance of that occurring. So that's an application of the geometric distribution. Now let us take a look at the binomial distribution. Alright, so now let us take a look at how the binomial distribution starts out. Suppose you have a sequence of n independent Bernoulli trials, and let x represent the number of successes in that particular sequence. We're going to be assuming that n is greater than 0, and also is finite. So n must be a number between 1 and some arbitrarily large number. Typically, n is not super large, like 5 million, because most of the time we cannot compute those by hand. There's usually some other distributions that we can use for those particular cases, but in theory we could still use binomial distributions if we really wanted to. But let us assume it's reasonably small. So what type of situations are we going to be looking at here? So let's look at a particular example. Let n be equal to 5, and let us assume we want to analyze the case where x is equal to 3. So out of the 5 trials, we're going to have 3 of them that result in success. That implies that 2 of them are failures. So sequence of 5, so we could have success, 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 failure, failure. We could have success, success, failure, failure, success. We could have success, failure, success, failure, and success. And there are several different more. So how many of these are there? So we should know that the order does not matter, therefore we should be able to use a combination to count how many there are. So there's going to be 5 choose 3 different number of ways you can have this type of structure, right? So of course that's going to be equal to 5 factorial over 3 factorial times 5 minus 3, the quantity factorial, which is just going to be 5 times 4, all divided by 2, which is going to be 5 times 2, which is 10. So there's going to be 10 individual elements of this particular structure. We're going to be assuming that these events are independent from each other, therefore the probability of SSSFF is going to be the same as that of SSFFS, because we have 3 S's and 2 F's, and multiplication is commutative. Therefore, the probability of this particular event, x is equal to 3, is just going to be equal to 5c3 times the probability of failure to the power of 2 times the probability of success to the power of 3. So this type of structure is going to build into what we call the binomial distribution. So let's just state the general formula for that. So the probability that capital X is equal to little x is going to be equal to n choose x, so that's the binomial coefficient representation of the same thing, 5c3, so ncx, of 1 minus p to the n minus x times p to the power of x. So this is what we call the binomial distribution. Nice little distribution, extremely useful. So 1 minus p, that's the probability of failure. P, probability of success. X, number of successes. N minus x, number of failures. and n minus n choose x is the number of combinations of that particular type of structure in the sample. That's pretty much the overview of the binomial distribution. So let's just state a couple properties just in case you need them. The expected value of x is going to be equal to n times p. So the expected number of people in a particular sample that will succeed is going to be equal to the size of the sample times the probability of success. And the variance of that particular random variable is going to be np times 1 minus p. So n times the probability of success times the probability of failure. Some people will write 1 minus p as q, so npq, but there's no need to introduce too many letters. We all know what 1 minus p is. So again, if you do not know how to derive these, you could use moment generating functions again to derive them, but we're not going to go into those details here. So now let us take a look at a particular example on how you can use the binomial distribution to solve real-world problems. So suppose 67% of a population likes rock music, and you select a simple random sample of size 5 from that population. What is the probability that at most 3 of the people in your sample like rock music? So firstly, we're selecting a simple random sample from a population. Most of the time, and in practice, that usually will imply that each of the values in the sample are independent from one another, provided that the population is significantly larger than that of the sample. But aside from that, how would we solve this problem? So we're going to begin by defining what a success is. So a success is going to be defined to be equal to, so since we're interested in the probability of liking rock music, I'm going to define that as like rock music. So do I know the probability of liking rock music? Yes, 67% of the population likes rock music, so that's going to be my probability of success. So we have an independent sequence, and what do I mean by sequence? We have 5 people, right? So, and we want at most 3. So let's write our problem down here. So n is equal to 5 in this particular case, and we want the probability that x is at most 3. So remember, for the binomial distribution, the minimum size is 0, because it's possible that no people in our sample likes rock music. It's possible. So it goes from 0 to n for the binomial. So this is the same as 0 is less than or equal to x is less than or equal to 3. So I can rewrite this individually in terms of its individual components. So therefore, this is going to be equal to the probability that x is equal to 0, plus the probability that x is equal to 1, plus the probability that x is equal to 2, plus the probability that x is equal to 3. And whatever I get, that's going to be my answer. So how would you calculate each of these components? So let's look at 0. So in 0, we're going to have 5 choose 0 different ways. So 0 people in this sample like country music or rock music. So that means all of them are failures by definition. So this is going to be equal to 1 minus p to the 5 minus 0 times p to the power of 0. 5 failures, 0 successes. So for this next term, this is going to be 5 choose 1 times 1 minus p to the 5 minus 1 times p to the power of 1. This is going to be equal to 5 choose 2, 1 minus p to the 5 minus 2 times p to the power of 2. So 3 failures, 2 successes. And lastly, px3 is going to be calculated via 5 choose 3, 1 minus p to the 5 minus 3 times p to the power of 3. Right? Some people will notate this in compact summation notation. So our final answer can be rewritten as the sum from k is equal to 0 to 3 of pxk. And you can use this in Desmos if you want to as well, or in Excel. So that's just going to be the sum from k is equal to 0 to 3 of 5 choose k times 1 minus p. What is my p value here? So that's going to be 0.67. So 1 minus the probability of success, which is the probability of failure, is going to be 33%. So I'm just actually going to write that here. So that's just going to be 33% to the power of 5 minus k times the probability of success, 0.67 to the power of k. All right? So you could figure this out either in summation notation or by hand. So that's just going to be equal to 5 choose 0 times 0.33 to the power of 5 times 0.67 to the power of 0 plus 5 choose 1 times 0.33 to the power of 4 times 0.67 to the power of 1 all the way down to 5 choose 3 times 5, 0.33, 0.33 to the power of 3 times 0.67 to the power of 2, right? So once you work out all of those calculations, you should get an answer of approximately 0.5325 as our final answer. So there's approximately a 53% chance that at most 3 people in your sample like rock music. So before I actually get into the last distribution, I just want to make a couple more comments on the binomial distribution as well. So we already know that the geometric distribution should be a decreasing function. You should be able to verify that just from the structure 1 minus p to the x minus 1 times p. 1 minus p is a number between 0 and 1, so when you exponentiate that number to a number larger than 1, that number should decrease as that number gets larger. So the geometric distribution will be a decreasing distribution, but the binomial is not going to have this particular structure. Actually, it's going to have a variety of structures depending on what the probability of success is. So let's just graph them, all of them, right? So remember, the minimum value of binomial is 0 and the maximum is going to be n, right? So n and 0. And of course it's discrete, so I'm just going to draw a bunch of dots here that are going to have some shape. So n, actually this is a little bit skewed. I don't want that skewed. What I want is that looks skewed too. How hard is it to draw a symmetric distribution? There we go. That looks pretty symmetric, right? So this occurs when p is equal to a half. And let's assume that's approximately n divided by 2. If you have something like this, so a skewed right distribution, again that's n, 0, n over 2, this occurs when p is less than a half. And when p is greater than a half, you can take a guess at what type of distribution we're going to be looking at here, right? So we're going to have a heavily skewed or slightly skewed left distribution, okay? So when p is close to 0.5, your distribution is going to be symmetric. Most of your successes are going to be around the center. This is going to be our skewed right distribution. That means most of our successes are going to be on the lower end of the spectrum, like 0 to 5 or something like that. And our skewed to the left distribution, which means most of our successes are going to be on the right, which means if you have a sample of like 50, most of your successes, or it's going to be highly likely that you're going to have like 40 successes or 45 successes or something like that. All right. Let's also mention one more thing, and that's going to bring us into the next distribution. Okay. So our binomial distribution, remember, is going to be px of x is going to be equal to n choose x times 1 minus p to the n minus x times p to the power of x. And what I'm going to do is I'm going to let p be equal to lambda divided by n. So clearly, as n tends to infinity, p is going to get close to 0. Now, why would I want to do that? That's another long story which I won't get into now. So what I'm going to do is I'm going to rewrite this expression using this lambda over n term. And here lambda is just going to be a positive number because n is a positive number. So for the probability of success to be positive and make sense, lambda should be positive as well. So once I make the substitution, I'm going to have that px of x is going to be equal to n choose x times 1 minus lambda over n to the n minus x times lambda over n to the power of x. Right? So that is my distribution written in terms of lambda. Again, what is lambda? I'll discuss that momentarily. So just as a little calculus exercise, here's a question. What is the limit as n goes to infinity of px of x for this expression? That is, what is the limit as n goes to infinity of n choose x times 1 minus lambda over n to the power of n minus x times lambda over n to the power of x? So, if you want to practice your little calculus proofs, this would be a perfect time, but you should see that this is going to be equal to e to the minus lambda times lambda to the x all over x factorial. So, this is of course a distribution, not the same as the distribution for binomial, but it is a distribution, and that will be the next distribution that I discuss in this video. So suppose you have some continuous interval of time or space for which an average number of successes, which we're going to call lambda, is known on that particular interval. Let x represent the number of successes in that interval of space or time, where each Bernoulli trial that occurs in that interval is independent of another. So, just as a little quick outline of what we're looking at here, let's assume we're looking at a bank or a store or a a grocery store, I guess is a good example. Let's say from 12 p.m. to 5 p.m., you know on average that, I don't know, 35 people come into this store between 12 and 5 p.m. on average. And let us assume that you want to know what is the probability that between 12 and 5 a.m. That the number of people that come into this particular store between these hours, given this average, is more than 37. Right? So how would we figure out this particular probability? So notice here that the possible values for x could be anything from 1 to all the way up to infinity. This is not bounded above. So this is a little bit different than the binomial distribution, right? Of course, 0 people can come into the store. 5 million people could come in the store. Not, of course, considering physical restrictions or anything like that. So what we can do is sort of use that little derivation that I talked about before with the binomial distribution by setting n to infinity, because that's pretty much what we're doing here. It's almost like the number of successes, but that upper bound is pretty much gone now, right? So it's a limited binomial distribution, which we're calling a Poisson random variable, or that random variable is going to be associated to a Poisson distribution, okay? So this Poisson distribution is given by px of x is equal to e to the minus lambda times lambda to the power of x over x factorial. So if you wanted, for example, to find the probability that exactly 37 people came into the store between 12 p.m. and 5 p.m., you could just do e to the minus 35 times 35 to the power of 37 all over 37 factorial. Of course, I'm not going to do that by hand. You could probably use a calculator to get that particular value, but that's how you would figure it out. So now let us use this Poisson distribution to solve a real world problem that's just a little bit more harder than this particular problem that I've stated here. Suppose an average of 4.6 people pass through security at a local airport every single minute. What is the probability that in any given minute, more than 5 people pass through security? So let us sort of break apart this problem and sort of understand why we're going to use the Poisson distribution in this particular case. First, in order to use Poisson, you need to know the average number of occurrences in some particular interval of interest. So we're given that the average number of people that pass through security is 4.6, and the interval of time that we're focusing on is every minute. Make sure you take note of both of these things, because this is going to be important. What is the probability that in any given minute, more than 5 people pass through security? Right? So notice here that the interval of time, given minute, every minute is the same. You need to make sure that the problem is not asking what is the probability that in any given hour, more than 5 people pass through security. That would be slightly different. Of course, if the distribution across every single minute is uniform, you can simply multiply that answer by multiply this average 4.6 by 60, and that's going to give you the average number of people that pass through security at a local airport every hour, right? Notice that's different than multiplying the probability by 60. Really big difference there, right? All right, so what do we know? So we know lambda is going to be 4.6 on an interval per minute, right? And of course the problem and that average is given in the same exact unit, so that's great. So we want the probability that the number of people that pass through each of these is going to be greater than 5. So notice it doesn't say anything about independence here. We're just going to assume, just for the sake of this problem, that these people are independent. If it's not independent, you probably couldn't solve it anyway because you don't know the distribution of the people. Of course, in realistic, of course, throughout the day, it does change. Maybe in the morning it's more dense than in the afternoon. Who knows? Let's assume they're independent, at least. Or maybe a family goes together or something like that. So the least number that's greater than 5 is going to, of course, be the probability that x is equal to 6, plus the probability that x is equal to 7, plus the probability that x is equal to 8, plus and so on. Now, a downside for the Poisson distribution, Poisson is not bounded above in terms of the values of x, unlike, for example, the binomial distribution. So if you want to find this sum without approximating, you probably cannot do it. Yes, the Poisson distribution does decrease to practically zero eventually, but unless you use numerics to figure out what is close to zero, you're going to have some errors in your answers. So the best way you can actually solve this is take advantage of the fact that Poisson is bounded below. So we can always approach this type of problem from the complementary perspective. So this is going to be equal to 1 minus the probability that x is less than or equal to 5. And this is bounded below because that's the same as 1 minus the probability that 0 is less than or equal to x is less than or equal to 5. Right? So what I can do is I can find each of those probabilities. So that's going to be equal to 1 minus the probability that x is equal to 0, plus the probability that x is equal to 1, plus all the way down to the probability that x is equal to 5, and evaluate that. So how would I calculate, for example, the probability that x is equal to 5? So I would do it the same way as I did before. So that's going to be e to the minus lambda. So lambda was said to be 4.6 times lambda to the power of x all over x factorial. So that's how you would calculate px5, and it's going to be similar for px4, px3, 2, 1, and 0. So once you add up all of those values, you're going to have that's approximately equal to 1 minus, what is that? It's going to be approximately equal to 6858, and then once you do the complementary perspective of that, that's going to be approximately equal to 0.3142. All right, and that's how you can calculate probabilities associated to the Poisson distribution. So those are the three basic types of probability mass functions that you probably can use in real life: the geometric, the binomial, and the Poisson distribution. There are, of course, several others, but we're going to talk about them at a later time. So for now, let's do some practice examples just to make sure you understand the material that we discussed today. See you later.